Hello again. My name is Artem Makoyan, and today I would uh, read a lecture about detection and segmentation in computer vision. Okay. Uh, First of all, let's talk about what is detection, what is segmentation. You know that there is classification task, yeah. Uh, Particularly for images. But today we will check more interesting case. Uh, when we do classification, we want to find information about whole image, and detection or segmentation give us information about parts of the image. Okay, first let's take object detection. Our task is to detect some objects. For example, on the left you can see image where cars are detected. Not only cars, potted plant, but let's see. Let's check cars. So the idea is to put the object inside a bounding box. Bounding box is a rectangle whose axes are parallel to sides of the image. Okay, so the output of detection model is a set of bounding boxes with objects inside. On the other hand, when we talk about segmentation, we want more accurate results. So you can see that cars are detected, but not with bounding boxes, but with masks. So each pixel has the color. For example, green color is for car, purple for human, and so on, and blue for background. This approach is more accurate, and we say that we not detect cars, but segment them. So that's by segmentation. It's more accurate result, but you can guess that it's a little bit harder. Yeah, if you have any questions, want to say something, it would be great if you will give feedback during the lecture. Is it okay for everyone?
Yeah.
Great. So it's not very hard, I think. Let's go. Okay, first let's talk about segmentation. There are different cases there are different tasks where we want different segmentation approaches. Okay, first, semantic segmentation, where each class of objects have own color. Yeah, when I say color, it's more easy to understand. But in fact, each pixel has a number. For example, 0 is for cars, blue color, 1 for humans, red color, and so on. So the purpose of semantic segmentation is to distinct different objects, different classes of objects. Yeah, you can see that we have two cars on the right, yeah, two parked cars, and for semantic segmentation we can't distinct them because they are merged, and this is the problem for some tasks when we want to find distinct instances. And for this, we use instance segmentation when we want to detect each object, not class of object, but instance. And now you can see that cars, we can separate cars. Yeah, each pixel knows for which instance it belongs. And panoptic segmentation merges two previous approaches. Yeah, it can. It's in fact it's sum of semantic segmentation and instance segmentation. We can distinct each instance, and we can distinct classes. Yeah, and for object segmentation, object detection, there's only one case. Sometimes in more interesting cases, we want, for example, three-dimensional bounding boxes for some tasks, but we won't talk about it today. Okay, let's discuss pros and cons of these approaches. Okay, first let's take semantic segmentation. Obviously, it's more easy than panoptic segmentation, and in fact, it's more easy than instance segmentation. It is so it's faster and easier. It's suitable for stuff and things. What I mean when I talk about stuff and things, the problem of object detection is that it can't, for example, detect the sky, because sky has a very complex shape, yeah. And if we put it inside a bounding box, the bounding box will include all the whole image. So for example, for a car, we can say that the shape of car is very similar to rectangle. Yeah, maybe the shape of human is similar to rectangle, but there is some stuff that is not. So this is strong side of semantic segmentation. It can segment different things, not only objects. But okay, of course, it has problems, and as I mentioned before, it merges instances. Okay, let's see. Let's check object detection. It's fast and easy. Distinguishes instances in opposite to semantic segmentation, but it's inaccurate. It's incomplete and suitable only for things. And finally, instance in panoptic segmentation, it is complete, distinguish instances, accurate, but it's hard and it's harder and slower than other approaches. Any questions? Okay. Let's do. I will ask some interactive questions. What do you think? How can we obtain a segmentation mask? Let's talk about semantic segmentation. Maybe you have any ideas?
How can we obtain what? Could you repeat the question?
Segmentation mask. For example, we have an image and we want to find all humans. So for each pixel, we want to say, is the pixel, is it a human pixel or not? It is not a human pixel. So something for each pixel, we want to make binary classification, in fact. So this means we will obtain mask.
We can just, and we need to obtain like mask. We can just use something like, I don't know, maybe something like RNN, and just no for each pixel.
Yeah. Okay. I will give a little help. First of all, we have an image, size, age, height, and width, W. First question. And 3 channels. First photo, but it's not very important. First question, what is the size of the output? What is the size of mask we want to obtain? We understand what is mask?
We want to obtain like, for each pixel, we want to obtain probability of classes, right? So it's like number of classes times h times v times w.
Yeah, that's right. So I think you know the two approaches. For example, if there are two classes, we can predict, let's say, probability of the class. So the dimension will be 1. Yeah, maybe no, it's not a real probability, but we will say like this. Or we can predict, for example, we can predict this after sigmoid function, yeah, because it returns numbers from 0 to 1. Or we can predict outputs with two channels. Yeah, first channels corresponds to first class, second channel to second class. Yeah, human and not human. And we would consider this output as unnormalized probabilities. What I mean, for example, if you have two numbers A and B, for example, these are unnormalized probabilities. Yeah, this is class 0, class 1. We can get from them probabilities. How? With softmax function. Yeah, because softmax output gives us tensor with some 1 and numbers from 0 to 1. So we can consider them as probabilities. As I said, these are not real probabilities, but for us it's okay. So, and after we can check whose probability is bigger. So in fact, if the first probability of 0 class is higher than 0.5 or lower, let's take easy case, take 0.5, and check is it a human or not. So the output would be H on W and two channels or one channel. Let's take one channel. It will be easier. So then what architecture we can take to obtain this? NADs. And what criteria? So what laws we can use? Let's start with laws.
What laws we can use? We can just, why not to use just like common loss functions that we use usually with classification tasks?
Yeah, exactly. We can use
like cross entropy.
Cross entropy, yeah, for each pixel, and then sum the result. Oh, take a mean. In fact, the mean usually is taken. Yeah, right. We take cross entropy loss for all pixels, take the mean, and we have a function. Great. Okay, and what about a model? What model we should take? Yeah, I will say that there is no right answer. You can
I don't know.
suggest.
Can't we use just something like CNN with several channels, and yeah, we classify it channel,
Yeah.
like
Why not? But there's a problem. Convolutional networks usually decrease height and width of tensor and increases number of channels. Increasing in number of channels is okay because after we can use, I don't know, one-on-one convolution and get from 1,000 channels, yeah, and we will get only one channel, yeah, or take only one channels from this 1,000. It's not a problem, but the image becomes smaller and smaller. How we can overcome this problem? In classic convolutional neural networks, yeah, for example, for classification, we use pooling.
Can we use padding or something? Pooling.
Yeah.
No,
we can use
can't we use padding, and then we just not reduce dimensions matrix.
Yeah. What should we do to not to reduce dimension? So what convolutional parameters should we take?
Like padding is like if we use, for example, stride 1.
Yeah,
stride
exactly.
1.
Stride 1.
Like
stride
padding.
1. And we should
and padding
take
like
the right padding.
Yeah.
Depends on kernel size. Yeah, take kernel size odd number and padding kernel size -1 divided by 2, or something like this. So the size of tensor would be the same, and we won. Yeah, great. So yeah, first I thought to take example. For example, for each pixel, we would use linear layer. Yeah, in fact, it's a convolutional layer with kernel size 1. Do you understand why? I mean that using the same linear layer for each pixel. Yeah, pixel is tensor 1 on 3, because we have 3 dimensions. Is the same that take convolutional layer with kernel size 1.
Yeah.
You can check it. What's the problem with this approach? Yeah, and after this, we will take one layer, for example, obtain mask, and say, okay, let's check. What's the problem with this approach? What you can say?
It's not efficient.
Only one convolution with very small kernel size. We can't imagine more efficient architecture, I think. Oh, what do you mean efficient? Memory time or quality?
Time. Complexity.
It would be much faster than previous approach when we have many convolutional layers with bigger kernel sizes. So
it's like one convolution. It's a bit strange because we
yeah, I understand.
We multiply. We not take like usually we take like several objects and we form like one object depending on like and here we just, it means that we just each value will multiply to something, and it's
yeah. Good answer.
like I mean these
I
values like usually we use, and values are like values are dependent on each other. They like depend on some other values, and here they're like independent.
Yeah, great. That's what I wanted to hear. Yeah, first you could say that only one layer, it's a linear model. It's not very strong. And you have only 3 training parameters, but it's not interesting. We can, for example, take many layers, but with activation functions between them. The problem is with receptor field. How do you did you hear about it, receptor field, on the previous lecture, for example? Don't remember. The idea is very simple. When you have many layers and we have kernel size more than 1, let's check kernel size 3 and tensor 5 on 5. Yeah, something like this. And as you said, usually in neural networks, outputs depend on several values. Yeah. So after we use kernel convolution with kernel size 3, and for example, and padding 1 and stride 1, so the size would be the same. The question on what values this output will depend. Kernel size 3, stride 1. Any ideas?
So like on a 3x3 matrix.
Yeah, right. On these values.
Yeah.
And we take this output and give this as input to the next convolutional layer with kernel size 3 and stride 1 and padding 1. and we will get new new output, and the same question. I will draw it here, so like this. On what pixels the center will depend on? And I mean, yeah, we had 0 tensor, first tensor, and second tensor, 2 convolution layers. Yeah. So as we said, the center depends on 3 on 3 square, and on what pixels this center will depend. I mean pixels from 0 tensor.
If we had like 3 times 3 kernels in both first layers, so
Yeah.
on a full like 5 times 5 matrix.
Correctly, exactly. So the idea is that we take center square, and as at the same time as before, we say that this square depends on these squares from first tensor. But each of these squares depend on 3 on 3 square. For example, this green square depends on 3 on 3 square here. Yeah, and that's why when we say about dependence on 0 tensor, we will cover 5 on 5 square for center. Did you understand? Is there maybe you have some questions, or is it easy? Someone? Maybe should I repeat?
It's like it's understandable.
Yeah, right. It's not very hard, but I don't know. Maybe my explanation was bad. So the idea is that when we have many layers, why is it good? Why the model is stronger? Not only because the function is more complex, it's not linear, for example, yeah, but also because on further layers, in one pixel, we aggregate information about some square around it. Yeah, it is about when we talk about convolutional layers, of course. Yeah, so this is a receptive field. Receptive field for the square is a set of pixels on which the square depends. So when we say, if we have a convolutional layer with kernel size 3, yeah, what's receptive field of this model? We say square 3 on 3. And when we say we have 3 convolutional layers with kernel size 3, what receptive field of this neural network? We will say 7 on 7. Yeah. And it is important both for classification and for segmentation, because in classification we finally have 1 or 2. The size of output is 1 or 2. Yeah. And obviously the value output depends on all pixels, so it's not a problem. But in segmentation, if the output depends only on 1 pixel, it can't be correct. Why? Not because it's mathematically incorrect, no. Because when you know only the color of 1 pixel, how could you say if it is a human or not? Of course, maybe you can say, oh, it's no brown color, then it's human's eyes. Yeah, but it's a very bad approach. Yeah, even human can't say can't classify pixel only knowing about its color. But if you use kernel sizes more than 1, you would know all about region around your pixel. And if you know a region, yeah, you have more chances to classify correctly. And the bigger is the region, the more chances you have. But of course, if you want bigger region, you should use more layers, and this is not very good. Moreover, or you can use more bigger kernel sizes. But the problem is that you can't aggregate information about a very large region fully inside one number. Yeah. So you have here something like trade-off. The bigger region, more your model knows at the end, but more information you lose about your region, because encode information about 3 pixels in one number or about 1,000 pixels. Yeah, obviously the second case is harder. So if you want to train a simple segmentation, you can use some convolutional network. Don't forget to check receptive field. Yeah, any questions? It's a very basic approach, and next we will talk about more complex architecture. Okay, clear all drones. Great. Let's go on. Let's go on. My bad. But what about detection? How to obtain bounding boxes after? How to extract bounding boxes from output from tensor? It's not very obvious, yeah? Moreover, let's check the picture. There are several approaches how to. Okay, there are several bounding boxes that are correct. For example, in the first image, and what bounding box should we consider correct? Even if we have labels, bounding boxes, yeah. We can, for example, if purple is our label, we predict a dark blue bounding box, and in fact they're different. But that's and in fact it's incorrect, yeah. But obviously both bounded boxes are correct. That's why we say that our bounded box is correct. It is close to ground truth bounding box. It is close to our label bounding box. So we need a metric, a distance between bounding boxes. This distance is intersection over union, IOU. How how we can calculate it? It's very easy. We should take two bounding boxes, find area of its intersection, and divide it by area of its union. Intersection over union, easy. I will draw a simple picture. For example, we have two bounding boxes, green and red. Yeah. All right, like here, the same. And finally, here we take intersection. Here we take union. And if boxes are close, you can see that intersection of union is big. If not, then it is small. Any questions?
But why do we need this?
Yeah, why do we need? Because when we have classification, for example, we have a label that it is a human, and we predict that it is a human. Obviously, human equals to human, so it's correct. But here we have a label, purple bounding box, and have a prediction, dark blue bounding box. And they're not. And how we can say if our prediction is correct or not? Hard to say, yeah. But now we say Okay, if IOU is higher than 0.5, then bounded boxes are the same. They bound the same object. If IOU less than 0.5, then bounded boxes are different, so our prediction is incorrect. Okay?
Yeah, okay.
Because we want to evaluate our model on some benchmarks to get some metrics, and IOU is, I think, the most popular metric you can use for object detection. And we will use it next in different things. Okay, let's go on. Another metric is average precision. Okay, we have an image. For example, let's return back many bounding boxes. And then our model somehow gives us many bounded boxes as prediction. So we have many predicted bounded boxes. We have many label bounding boxes or ground truth bounding boxes. How we should evaluate our result? Yeah, because intersection over union helps to evaluate a pair of bounding boxes. But if we have two sets of bounding boxes, what should we do? Well, let's take one label bounding box and find all bounding boxes that are close to it. How to do this? Find all bounding boxes, predicted bounding boxes, whose intersection over union is more than the threshold. For example, more than 0.5. Yeah. And now we can count simple metrics for classification. Because if we found a bounding box that covers a label bounded box, we can say that it's a correct pair. If some label bounded box is not covered, it is an incorrect pair. And we can count true positive, find number of true positive pairs, false positive, false negatives. Maybe it's not correct to say pairs. Let's say true positive labels, or covered or not. So we can count true positive, false positive, and so on when we have two classes, for example, yeah. Usually, for example, here cat and dog, yeah, and the same we can do with bounding boxes. Here are some examples. For example, we can see that this is an incorrect pair, false negative and false positive, yeah. It depends on which class we take as 1 and which class we take as 0. This is false positive because they should be the same, but they're not the same. And where is a good example? Yeah, true positive, two cats are the same. False positive because the cat is not covered. Yeah, because the cat is predicted, but it's a false positive. There is nothing. There's no label here. And this is false negative because label is not covered. Okay, so we can count true positives, false negatives. After that, we can count precision and recall. Do you remember these metrics? They were, I think, last year when you talked about classification. Yes, okay, yeah. You can find formulas here. So we can count precision and recall. Okay, when we have precision and recall, we have a problem here. Why? Because all these metrics depend on threshold. If we take threshold 0.75 within one precision, one recall. Another threshold, one precision, one recall. Well, in fact, you can check that true positive, false positive, and false negative are different, but no. It's okay, because you can see, for example, for this threshold, 1 divided by 3, and for this 2 divided by 3, they're different. But for dogs, they're the same, but it's occasionally. Yeah. So the result depends on threshold. What threshold to take? If we take very, very big threshold, then even for close bounded boxes, we will say that intersection of a union is less than 1, for example, if we take threshold 1. Then precision will be very, very high, recall very, very low. Otherwise, if we take intersection of union 0, so even this pair will be positive pair, because intersection of a union will be more than 0. And then the opposite way. I don't know. Okay. What should we do? What threshold should we take? For this, we draw graphics. We make, first of all, a table for different thresholds. We count different recalls in precision. So you can see for high thresholds, recall is usually small, and precision is usually high. And in opposite, for small thresholds, the situation is opposite. As far as I remember, there is not the rule that the curve should be distinct. Yeah, you can see that there's no, as far as I remember, there's not the rule that here we have, here the values increase and here decrease. This for, no, all this was for rock oak. So maybe someone remember? Or it's hard to keep in mind such things.
There is some strange formula. There is something like root of all of.
Have you heard about precision recall curve before?
Yeah.
Great.
And about rock oak as well, but I don't remember like what is rock oak.
Yeah, as far as I remember, what's recall? You can check correct predictions divided by total ground truth. So, we can say that precision is what first thing you. There's a rule how to remember what is precision and what is recall with your intuition. Precision is more about snipers, yeah, because they should be precise. So each shoot should find its target, yeah. And for recall, it's more about, I don't know, have you played games? About guns, I don't know. When you don't need each of you shoot to find its target, but you want to cover as much as you want. So precision needs to be precise to and recall should cover as much as it can. The bigger recall, the more you cover. Cover what? Cover classes, objects with class 1, and the bigger precision, the less you miss. So when you say that someone is 1 and it is 0, it is a miss. In fact, it's false positive. Yeah, because it may be a little hard to remember all of this stuff, but if you have some rules in mind, it's more easier. Okay, so fair curve, it goes from left to right and decreases. So what is this? As I said, you make a table with different thresholds, and on x-axis you have recall, and on y-axis you have precision. And you take all points, recall precision, and make these points, and you have a curve. Okay. For example, we have recall on 0.1 and precision 1. So we take on axis 0.1 because it's recall, and take on precision axis 1. So this is the point, first point for threshold 0.95. Yeah. And you can count average precision. It's a little, there is maths, but you should count the area under the curve. It's average precision. Easy, yeah? So the rule is simple. Ideal situation when you have a curve like this. This means that you have a point where recall is 1 and precision is 1. That's great because you don't miss and all your guesses are right. So, and here you can see that the area behind this curve is 1. So the bigger average precision is, better is for you. And for example, this case, whereas it's linear, average precision is 0.5. And this corresponds to a model that guesses in random. Let's say that sample is class 1 or class 0, 0.5 probability for 0, 0.5 probability to 1. If you have curve like this, is it good or bad? What do you think? Okay. This is very good. This is a random model, so very bad. And this is lower than random model, 0 average precision. So you didn't guess even one sample. But if you have questions with 2 answers and you run in all of them, what does it mean? That means that you can change your answers and your model will be perfect. Yeah? So the idea here is that if you have classification problem with 2 classes, the model lower than 50% is very foolish because you can guess in random and you will get 50%. If you have a model that guesses in 20% on 20% answers, inverse it and you will get a model that guesses 80% answers. So in fact, when we talk about bad model, bad average precision, we talk about linear curve. Okay, this is our metric for detection task. We count precision and recall, draw curve, and count area under curve. But there is a small problem. What does it mean to draw a curve? For this, there are different approaches. For example, we can, here you can see a curve. Yeah, this one. Let's take red. And we approximate it with rectangles. You can see that you see here points, and we have the same points here. This one, yeah. And let's approximate it with rectangles and count the area of these rectangles. For example, you can check here, the error will be much smaller if we have many samples, many objects. Okay, many thresholds. Okay, how to count the area of this square? Who knows what is the area of rectangle? Sorry, not square, rectangle.
That height times width.
Yeah, right. So we should count width. What is width? Remember that these points, x-axis is recall and y-axis is precision. So the width is recall of this point minus recall of this. So we should sort all recalls, yeah? When we sort points and take recall of k minus recall of k minus 1. its width, and to multiply it on the same maximum of precisions, because first precision is equals to this, and second precision equals to this. So maybe the curve would go, I don't know, some another way, and right would be bigger. But for me, I would prefer to count area of trapezoid, if I correct with the name. Yeah, it's half sum of parallel sides multiplied on width, because if we have trapezoid with right angle, 90 degrees, yeah, the formula is easy. A plus B divided by 2 multiplied by H. Am I correct?
Yeah.
Great. But in fact, you will use library functions. So, but it's always great when you keep in mind how it works inside. Okay, the hardest part, I believe the hardest, is gone. And if we have many classes, even if we have 2 classes, you can see why we have here precision recall for cat and precision recall for dog. That's because when we count precision recall, yeah, our classes are not equal. We have 0 and we have 1, and we try to guess first class. So when we check true positive, false negative, they depend on what class is 0 and what class is 1. So what should we do? We can say something like, let's assume that cat is class 1 and dog is class 0, and count precision recall, then count average precision, yeah? And do the same with dog. But for say that dog is class 1 now and cat is class 0. But now the values will be different. You can see that for cat, for example, we have these values, and for dog we have these values. So the average precision will be also different. When we have 10 classes, we do the same. Take each class, we'll take each class and say that it is 1 and all other classes are 0. And count average precision. We have 10 classes. After that, we have 10 average precision metrics. What metric should we do? What should we do with these metrics? We should take mean. We should sum them and divide on a number of classes. K is number of classes. That is named mean average precision. Not very hard, yeah? Any questions?
How do we detect, like, if we have several like, how does it called bounding squares? How do we choose which? I just didn't get how. What did we do now? Like which?
If we have several bound boxes that cover labelable box.
Yeah.
Great question. It's our next slide. Yeah. You can see here we have a photo and many bounding boxes covering the face. That is the right answer. But what if we will forget about neural networks and say, like, let's take every bounding box we can draw, every millions of bounding boxes. And that's why all classes would be covered, and we have very high metrics. Yeah, that's a problem. So we need a process that will move from left image to the right image when we have only one bounding box. The idea is very simple. If 2 bounding boxes have high intersection over union, that means that they are close enough to each other. That means that we can drop one of them. Not very hard, yeah? I would like to also mention that for each bounding box, let's also predict score. It's something like score that bounding box is correct. For example, we want from our model to score high for bounded boxes that are correct, and for incorrect bounded boxes, score low. So let's sort in descending order corresponding to their scores, and make this next process. Take bounded box and drop all bounded boxes that are close enough to it in terms of intersection over unit. Not very hard. Okay. Any questions about non-maximum suppression? That name's non-maximum suppression or NMS. I believe that it's not very hard. And finally, we have metrics. We have non-maximum suppression. To get a good answer, let's talk about ideas. How we will obtain these bounded boxes finally. There are different ideas, but the first one and the most simple is to divide our problem into two parts. First part is generate bounded boxes proposals. So the first part of the first model proposes many bounded boxes. And the second bounding box will score these boxes. And after that, we will get many bounded boxes, even bad bounded boxes, but with bad scores. Or good scores if it is a good bounding box. And after we will filter and, for example, drop all bounding boxes whose score is less than 0.5. I don't know, something like this. And do non-maximum suppression, and we'll get the answer. Okay. This is the idea. Region proposal, propose regions, propose bounded boxes. Another idea is bounding box regression. Predict the coordinates of bounding boxes. Yeah. For example, let's say we want to predict 100 bounding boxes. So the output of the model would be tensor 100 on 4, because each bounding box has 4 coordinates. Sorry, not 4. We also want to predict score, so on 5. Something like this. Sometimes we want to predict something more, for example, classes, yeah? If we want to not only detect objects, but also classify them. Then we will predict probability for each class, for example. Yeah, and another idea is sliding window. We will say that, let's take, for example, bounded box 10 on 10, and take all windows inside an image 10 on 10. And for all window classify, for all window classify is there is something is okay for all each window we will score, for example, yeah, and do the same process. Drop all low scores and left big scores. This is ideas. We will see them next in architectures. Any questions? Okay, finally, I will talk about different neural networks. Mostly, I will cover main ideas, but you always can check and read more details about that. First is RCNN. As I said, there are two parts. First part proposes bounding boxes. Second part classify, for example, classify each box. In vanilla approach, the proposals were were made not with machine learning. There were classic algorithms. The idea is to, for example, join pixels with the same color, yeah, and then we will get regions of the same object. Because, for example, we will get region of shot, region of head, region of face, and big regions will be covered by bounding box, and this is a proposal of bounding box, something like this. That's not very interesting because it's an old algorithm. No one uses it now. But after we take all regions and put them as input to classification network, some CNN, for example, and it classifies what class is it, or maybe it is nothing inside. So here is a person. Next was fast RCNN.
How do we extract region?
Yeah, propose regions, you mean?
Yeah. Propose region. Yeah.
It's yeah, as I said, it's an old algorithm. I wouldn't talk about it, but the main idea is to join pixels with the same color, with a similar color, into one big region. So after this algorithm, there will be one region of short, for example, one region of head, because they have similar color. Yeah. If you know algorithms, for example, you can do something like DFS or on pixels. Another region would be horse, yeah, trousers,
yeah,
and then we will put each region into a bounding box. It's not very hard. It's algorithmical. There is no machine learning. That's why it doesn't work very good. Okay.
Yeah.
Okay. Let's continue. Fast RCNN. The main idea is that we spend very much time. We spend much time extracting each region, each bounding box, and put it as input to a convolutional network. Where we can do faster. The idea is that convolutional network first extracts features. For example, it continuously apply several convolutional networks, and we try 5 times. Yeah, and after it, we will get tensor height divided by 32 and width divided by 32. And each pixel of this tensor contains information about receptive field, as I said, yeah? So we extracted some feature map. There's names feature map. You can say conv feature map. Why feature map? Because each pixel contains feature about a region from original image. And the idea is that if two bounding boxes are close to each other, then most of work will be doubled, because the intersection, yeah, when we take convolutional kernel, is the same for both images, and we double the work. So first we take the image, extract feature map, and when we have proposal of bounding box, we project its coordinates on our feature map, in fact, divided by 32, something about like this, not very hard maths. And only after we take feature map, and only after we put it to input of rest of the convolutional network. So our CNN contains first feature extractor, like this. And after classification head or something like classification tail, something like this. So before, RCNN took each region, each bounding box, and put it as input first to feature extractor and then to classification head. And now we put the whole image to the feature extractor only once, and after for each bounding box, we put the extracted feature map for this bounding box to classification head. And the classification head has much less parameters. It's much faster. So this is fast RCNN. Did you get the idea? Maybe some parts is too hard.
Can you like shortly explain again?
Okay. again, before we had CNN, yeah? CNN consisted of two parts: feature extractor that takes image and returns a tensor with height divided by 32, for example, and width divided by 32, but more channels, yeah? Yeah, the standard here. And after, for example, we got pooling, yeah, pooling layer, and made classification, yeah. And before we took each bounding box and put it first to feature extractor and then to classification head. Another region, another bounding box to feature extractor, then to classification head. But we can do it faster. How? Because if we have, for example, two bounding boxes that intersect and do, for example, one convolutional layer, apply it to it, then for this region, for intersection, the result would be the same because here are the same pixels. But before we took each and process independently and double and do the work and we did the work twice. Do you understand? We do understand why twice?
Yeah.
Because for this intersection twice.
Because we just classify 2 times the same region.
And not classify, but extract features of the same intersection region twice. Extract features. But because classification is more hard, because when we do pooling, then for each region, if they're different, if they're not exactly the same, we will get different values.
So
but
like we have
feature extractor for
feature extraction is just like a convolutional layer. It's without pooling.
Several convolutional layer. Yeah, without pooling. So in fact, we will obtain exactly the same values for intersection. Okay?
Yeah.
And now let's do something like this. Put the whole image to image extractor, take bounded box, and in fact, if we will cut the bounded box from the image and put to a feature extractor, we will obtain the same red tensor, exactly the same. Do you understand why? Because it's convolutional layers. So we can skip this feature extraction for each bounding box and take and cut a feature map from this. Okay? Yeah, and I also want to say that because we divide the width and height on 32, the coordinates of bounding box may be bad. So we have extra head that regresses box coordinates, as we said. So it only refines bounding boxes. So when we have proposal of bounding box, let's also use something like MSE mean squared error loss on predicted corners and label bounding box to refine bounding box. So we predict also coordinates of corners. Okay.
We predict only corners of bounding
box?
We
predict corners and bounding box is the same. I mean, coordinates. For coordinates, this is the same. Then bound is the same with bounded box. Because the problem is that proposals of bounded box are done without machine learning. They can be bad. So let's refine them a little. Because we need little offsets. Because in fact, bounded box is not very bad. But maybe we want to take like this, yeah, it would be better, something like this. Okay?
Okay.
Let's go on. Faster RCNN. Wow. Well, the idea is next. Okay, we're tired of not machine learning proposals, hard algorithms, similar pixels, many cases where this doesn't work. So let's use NCAS. What is NCA? the idea is very, very simple. For each pixel, let's generate a set of bounded boxes with the center in this pixel. For example, 3 on 3, 5 on 1, 1 on 5. So we have this size named anchors. Yeah. So for each pixel, we can generate many bounding boxes and do the same. We have proposals, we classify them, and we obtain bounding box if the score is good. Yeah.
What did we do? We create anchor boxes and then
this named sliding window. For example, we have anchor boxes 3 on 3. We take each pixel, draw 3 on 3 with center in this pixel, and say that this is our proposal of bounding box.
Yeah.
Then we take 2 on 5, 5 on 2. Take each pixel, draw 2 on 5, yeah, and say that this is our proposal. So something like this. Okay. Mask RCNN. The idea is the same as previous. RCNN, not faster, I think fast RCNN. But we won't get segmentation masks. So as I said, we first count feature map, extract feature map, classified box. But after, for each box, we up sample the image, and for each pixel, make segmentation for each box. In fact, we took the previous architecture where we predicted bounded boxes and say something like for each bound box, let's make segmentation. Not very hard. But there are some details that first of all, as I said, when we when we obtain feature extractor, our dimensions are lower, divided by 32. So our mask can be in fractional points, yeah, not in fractional points. So we should understand what is the color of pixel of this mask in fractional point. We can use line interpolation for this. Take 4 corners of a square in feature map, and count distances and count weighted sum, weighted by these distances. I understand that this is not very obvious what I said, but I want you to understand the ideas. So I want, because we don't have enough time to go into details, but you can always, I have links in slides. You can always go to paper and read about it. Yeah, sorry, because we have much material. After, all approaches before had to first generate proposals, and after classify them. A new paper, the idea is to make these 2 steps in 1 step. One model will classify, unite all models for proposals and classification. Yeah, in fact, the idea is the same. The architecture you can see on the right, but in fact, it's very similar. What's new? That we do anchor boxes on different scales. Because what's the problem? On the image, we can find small objects and big objects. And if we take anchors small, we wouldn't cover big objects. And if we take big, then big bounded boxes would be very bad for small objects, and we wouldn't cover them also, because intersection of a union would be very bad. So we extract, we do anchor boxes on different scales, of feature map, because, for example, divided by 32, then divided by 64, And this means different scales. You can see on the right, yeah? There's smaller feature maps. And the smaller feature map, the more receptive field, and the more information it contains about big bounding box. And the bigger feature map, the less receptive field, and each pixel corresponds to a small object. Okay. Okay. And finally, let's talk about UNet. We discussed architectures for detection, but what about to improve architecture for segmentation? It's a very, very popular model. It is used even now in many tasks. What is the idea? Let's remember about receptive field. Yeah, on last stanzas, last outputs of layers, each pixel has a very, very big receptive field. And this is good. But when we do segmentation, we can't use straight, yeah, higher than 1, because we'll lose the size of original image. But that's not true. We can use straight 2 and higher. Oh, we'll use straight 2. How? If we decrease the width and height, then we should invent how to increase the width and height. And that's not very hard to do. Give me a second. If we have, for example, tensor 2 and 2, what about to make tensor 4 and 4 and put color of, for example, of this pixel on 4 of this? That name is upsample. Or we can make something like linear upsample, yeah? Put between these 2 pixels something like average of them. Yeah? The different approaches, when we put the same color, there's names nearest flag, here linear flag, there's cubic flag, bicubic, quadratic. That's not very important. The idea is we can increase the height, the width and height of the tensor. So first, let's go down, obtain, for example, a very, very small feature map, but with a very, very big receptor field is important. And after, go up and obtain the original size. Why is it good? Because we can't, for example, if we have size 64 and 64, and want a big number of channels, and this will take much more memory if we have size 2 and 2 with the same number of with the same big number of channels. So this trick helps us to get big receptor field with a big number of channels, and then go up and obtain segmentation map. But there is a little problem. When we go down, we lose information, local information, because each step if you remember, I said that big receptor field is good, but we can't put information about 1,000 pixels into one pixel. So we lose information, but it is very important because segmentation is more about local information, because you need answer for each pixel. Because if you have classification, you don't need information for each pixel. You should only need information either as a dog or a cat. But here you should answer for each pixel, classify each pixel. So to get this information back, we after upsample, we take the corresponding tensor and stack it to our current tensor. So what I mean, we divide our model into encoder and decoder. The idea is that the encoder encodes the information about the image into a small tensor, and the decoder decodes this information into the original image. In fact, into the mask of the original image. Encode and decode. But of course, from small tensor, you can't get the information about a big image because you lost many local information. So you, on each level, you take the corresponding tensor from encoder, from output of encoder, and stack it to your current tensor. So you remember about information from this level after encoder output.
Isn't that just attention mechanism?
No, it's not attention, because attention is more about when each pixel looks into every another pixel, and here the idea is there is another idea. We want to take one big tensor, compress it into representation like this, and then uncompress it into mask. This will help us to make memory to spend less memory, spend less time, because smaller height, smaller width, smaller tensor, fast operations, less parameters inside the model. But you don't lose information about local information because you use skip connections. This name skip connection. And the layers are the same, convolution layers. So convolution with straight 2, and for decoder you also use convolution, but also up convolution or upsample.
Again, how do you stack like the layer, like this layer 128 times 280 with like layer 100?
Good question. Maybe the wrong numbers. Usually the size is the same because you divide the size twice, and then upsample twice. For example, if you had 128 height and width on first layer, on second you will have 64, 32, 16. Here again 16. You can use skip connection, 16 with 16, then 32, and etc. Sorry, maybe I chose the bad picture. But it's idea. Even if you have different sizes, you always can use some convolution before skip connection to make the sizes, for example, the same. Yeah, we have 280. You can use some convolution with big kernel size, for example, I don't know, or pooling, to make the tensor 200 on 200. But it's a little strange, to tell the truth. It depends on task, on data, so it's okay. That happens. But usually, as I said, you divide by 2 and upsample by 2. There might be some problems if the site is odd. But as I said, you can use some convolution, or before the task, you can pad the image to make the site degree of 2. For example, if you have image 100 on 100, pad it with 14 on each side, and you will get 128 on 128. It's more about practice, more about technical tricks. But the main idea is to use keep connections to remember local information and to use encoder-decoder structure to compress the information, but extract local information, global information, and then decompress it with decoder. Any questions? Not very easy, but not really hard, I think.
It's okay. Yeah, it's
I think we have written UNet, but I think everybody is tight because it's 7 minutes before 1 hour and 30 minutes. So I think we will end here without reading UNet, but you can always read about it. Any questions? Any feedback? I don't know.
No, thank you for the lecture.
Thank you for your interest. Okay, then have a good day.